So let's explore the topic of luminosity. Luminosity is the amount of energy per second that an object exists. You might say it's the amount of light that the object exists, except that not all of the energy is in the visible spectrum. It could be in other parts of the electromagnetic spectrum, but it's still energy. So that we say that the luminosity is the amount of energy per second that an object exists. Now, we have two types of luminosity. First, the absolute luminosity, which is the actual amount of light or energy that an object exists. And then we have the apparent magnitude of that luminosity, which also involves how far away it is. For example, if here I have two flashlights, and it's clear that the large one is quite a bit brighter than the small one, and that the absolute luminosity of the large one is many, many times the absolute luminosity of the small one. But yet, if I was to take the large one and move it 10 miles away, then the small one, being closer, would outshine it. So apparently, the small one would be brighter. And such is the case when you look up at the stars at night. The brightest stars might not be the ones that have the most absolute luminosity. It just might be that they're closer to you, so they appear brighter. In order to know what is the absolute luminosity of one star compared to another, they would all have to be the same distance away. So what we're going to investigate now is how do you determine what is the absolute luminosity of a star or any other object. If I have 1 square meter of surface area, and that 1 square meter is at a temperature T, then it will emit an amount of luminosity that is equal to some constant sigma, which mostly depends on the units that you're using, times the temperature to the 4th power. So it's extremely temperature sensitive. That is, if you double the temperature, then the amount of luminosity goes up by 16. If you multiply the temperature by 10, the amount of luminosity goes up by 10,000. Now the constant sigma is equal to 5.67 times 10 to the minus 8 in the units that we're using, and in some other units it might be equal to a different value. But now let's take a larger surface, and suppose this surface is some now rectangle, and suppose it has 5 meters on this side and 4 meters on that side, so it is divided up in a fashion similar to this. And now if we take 1 square meter of that, we know that the amount of luminosity is sigma t to the 4th. But that's true for every square meter that is on this surface. So the entire luminosity that would be generated by the entire surface is equal to that which is generated by each square meter times the area. In other words, the number of square meters that are in the surface. So here it would be sigma t to the 4th times 20, because there are 20 square meters in the surface. So the amount of luminosity that comes off an object depends on two factors. One, what is the temperature of the object? And two, how many square meters are in the area that's doing the generating? So let's take a circular hot plate, such that you could use to heat up your dinner on. And it would look something like this. It would have a container, and on the surface of the container would be your circular hot plate. And suppose it has a radius of 5. Now, if you heat it up to a temperature of 4, then the amount of luminosity that's going to come out is sigma t to the 4th times the area of the hot plate. But the area of a circle is equal to pi r squared. So it would be pi times 5 squared, so it would be 25 pi. So we would multiply the temperature of the hot plate by the amount of area that's in the hot plate, which is 25 pi, and the product of that multiplication would give us the luminosity that was coming out of the entire hot plate. Now, if we take a star, which is a spherical object, so we have a spherical object, and it indeed is a spherical object. Now, the spherical object has a surface area. And if r is the radius of the sphere, of which is the surface area, then the surface area is equal to 4 times pi r squared. So pi r squared for one circle, but if you're looking at the entire surface of a sphere, the entire surface area of a sphere is given by 4 pi r squared. Now each one of those square meters would radiate sigma t to the fourth. So the total luminosity that would be radiated by the entire surface of the sphere is sigma t to the fourth for each square meter times 4 pi r squared for the number of square meters that are in the surface. So you see that the luminosity of a star is determined by two factors. One, what is its surface temperature? And two, how large is the surface which is doing the radiating? So if you increase the temperature, you get more luminosity. If you increase the radius, that is, you increase the surface area of the star, you get more luminosity. If you increase them both, you get terrific luminosity. But if you increase the temperature, but reduce the radius, which is a type of star we call white dwarf, then you don't get so much luminosity in the total. And if both of them go down, you have a low temperature and a low radius. That's what we call a red dwarf, a very small star that doesn't have much luminosity. Then the luminosity goes way down. So this is our luminosity law, and the important thing to remember about it is it has two contributions. One, what is the temperature of the star? The higher the temperature, the more luminosity. And two, what is the surface area of the star? The more surface area, the more luminosity.